Hi again, and welcome to the third video on the life insurance setup in chapter 3.3. So what we will look at now is the term insurance, and here we will start using the symbol capital B capital B of T to denote denotes the benefit that is paid out at time T. Now you might note that this reminds you a lot of the lowercase b that you used in chapter 1, and rightfully so, because the only reason why this b is a capital B is because we use the big letter to denote that this depends on something stochastic, because it depends on the lifetime, so it depends on something stochastic. So that's the reason why we use capital B. Now, if we just take a look at the case of the term insurance, then what do they tell us in the book? Well, in the book they tell us that a term insurance with expiry N, so they actually say that lasts in years. So a term insurance with expiry N pays 1 at time T if the person dies between T minus 1 and T, or else it pays 0. So if the person dies between T minus 1 and T. So they actually write up the I actually think they do write up the expression for B of T, which they say is equal to the indicator function of death occurring between time T minus 1 and T, where T goes from 1 to 3 and so on up to N. So this is the term insurance. Now, how does the payment stream for the term insurance look if I were to draw the payment stream? Well, that kind of depends on when the person dies, right? So let's take a look here. At time 0, the person is X years old. And then let's say N expiry is here. Now, if the person dies after time N, so let's assume that Tx is greater than N, then in such a scenario, the person will not have earned any money from this contract. So the insured will just have lost all of the money if the person pays premium into such a contract, because in such a scenario where Tx exceeds expiry, there is no situation of T where Tx lies between T minus 1 and T. And this scenario occurs with the probability 1 minus the survival probability. Oh no, sorry. This scenario occurs with the probability NPX. So in this case, as opposed to the pure endowment case, it's actually a really bad thing if you die after the expiry date, because then there's no money. So let's take a look at the other case where the insured dies before the expiry date. So let's say that that the person dies at this time, right? Then if we have T here and T minus 1, T minus 2, and so on, and then T plus 1, then if the person dies here, that means that there is, so if this is Tx, then that means that Tx lies between t minus 1 and t, and then there's a payout of 1 exactly at the end of the year where the person has died. If the person had died between t minus 2 and t minus 1, then the payout would have been here instead at t minus 1. So this occurs with, well, well, what's the probability that this occurs? The probability that this occurs is the probability that the remaining lifetime lies between t and t minus 1, right? So that's the probability that this will occur. However, as opposed to the pure endowment case, it's not enough to just look at these two scenarios, because the thing is, the person can also die at time t minus 1 and t minus 2. And then in that case, that would occur with the probability of Tx lying between t minus 2 and t minus 1. And so on and so on. So we already now we can kind of see that this situation is a bit more complicated than we might have anticipated. And so this is why I think it's a good time now to bring in the formula for the expected present value. So the expected present value of future benefits. So the expected present value of future benefits is denoted by v of 0. And it is equal to, if you take b of t at each of the future time points. So if you take every single payment at time 1 all the way up to time n, which is the expiry date, and for each payment at each specific time, you discount it back. So you discount it back to time 0 by multiplying by the discount factor e to the minus delta t. If you do that, then what you get is you get the present value of the payment stream, right? However, it's not enough, because b of t, as we see quite clearly from this attempt to draw up the payment streams, b of t depends on the value of tx. So this will not give us a number. However, we do get a number if we take the expected value here of b of t. Now, often this is just where we end. However, because this e to the minus delta t is not stochastic, we can just go one step further and say we take the sum outside of the mean value, and then we take the discount factor outside of the mean value, and then we just have the mean value of b of t inside here, right? So this is probably something you guys have not learned yet, but whenever you have a sum and the mean value operator, you can always interchange them. And since e to the minus delta t does not depend on anything stochastic, we can also take that outside of the mean value because it's just a number that's multiplied onto the mean value. And now what we have is the mean of b of t inside here. And b of t is equal to this thing, right? So we can do some more calculations, and then the book will actually give you how this is equal to this thing here, and you can find the expression for this thing in the book. So this is the present value of, the expected present value of term insurance. That was the part about the term insurance. Now these videos are kind of running a lot longer than I had anticipated. So if you feel like you've already got the idea, there's no reason for you to watch the next video. You can just kind of skip to the solution. But if you also want to see how we can draw the payment streams for the annuity case, then just watch along in the next video as well.